Welcome to a lesson with Dr. Powell. Let's take a look at another example of a verifying that a limit statement holds, a rigorous limit statement holds. Okay, so let's suppose that we have limit as x approaches 5 from the left side of 1 over, and let's do 1 over x minus 5. Okay, what is this going to be? Now, x is a little bit less than 5, so it's going to be negative, and it's going to be close to 0. It's going to be negative infinity. All right, let's verify this using a rigorous limit statement. All right, so let's first write out what the statement is. Given now for the y value, we're going to have an m for position because this is going to be low here or going downward to infinity. So given m, then we can say there exists a delta greater than 0 such that if, now here we don't use absolute values because they're only going to be in one side and we want whatever we write to be positive. And since x is to the left, 5 minus x is positive. So less than delta. So if that is true, then what's going to be true? Then, well, f of x is going to be going to negative infinity. So that means it needs to be pushed lower than our y closeness idea, which is to infinity, which is just a position. It's just going to be less than that position. So getting pushed downward to negative infinity. Okay, so this is the statement that we'd like to verify. All right, so let's draw a picture, and what we're going to do is we're going to find that delta. Okay, we're going to find that delta here. So let's draw a picture of 1 over x minus 5. Now this is a transformation of 1 over x to the right 5. So we can think of a picture here. X equals 5. All right, so it looks like this and this. All right, so going down that way. Now, okay, we can think in a picture. All right, so given m, so instead of epsilon, we're just going to pick a point m here. So m and draw a line here. So, and then we need to find, in fact, for the sake of our picture here, with the lines being so close together, I'm just going to emphasize things a little bit. So let's just suppose we have, okay, let's just kind of do that just so we can kind of see what's happening a little bit. Okay, so our delta, so what delta value should we pick? We want, and what is our box really looking like? Okay, so our box is basically everything down here. So it's kind of like an infinite box extending down this way. And we're going to narrow it in with the delta. Now, if we chose a delta out here, oh, and this is interesting because this is a one-sided limit. So that means our box is one-sided from the center. So you see how we're going close to 5 here? And since it's a left-hand limit, we're going to ignore everything on the right. So really the box is kind of half of a box in some sense. We're not going from the center symmetrically. We're just going from the center in one direction. So from x equals 5 just to the left. And we want to pick a delta. Now, if delta went all the way out here, that would be an issue because why? Because the function is outside of the box right here. Now, if on the other hand, we had drawn delta over here, that would work because look, the function is completely contained in that box. So this would be the box here that we'd be concerned with. And it goes that way forever, and the function is completely contained in it. So that would work. Well, to find a delta that would actually work, what we do is we usually find the worst possible one, which is at the point of exiting. So right here's the point of exiting, right there, kind of the intersection of the curve itself with the the y value that represents the edge of the box. So in this case, y equals m. So we just need to figure out the delta that takes us there to that location. Okay, well, we know a few things. We know the y value at that point. Do we know the x value at this point? Let's see what it is. In terms of delta, well, we know we're at 5 here, and then we go delta that way. So it looks like it's 5 minus delta. Okay, so the x value at that point is 5 minus delta, and the y value is y equals m. Now, what relationship do we use between the y and the x value? Precisely the function itself. Y equals that. Okay, so this is the relationship between the x and y value because this point is on the line of the curve of the function. That's described precisely by that. That's described precisely by that point right there, that intersection. So we can plug in 5 minus delta for x. We can do that. 5 minus delta, and we have a minus 5. All right, and then that is going to be equal to the y value, which is m. And then we solve for delta. All right, so we do that, and then we can take a reciprocal of both sides. So m is equal to negative delta, and then multiply both sides by -1. So delta is simply equal to, let's see, hold on. Take reciprocal of both sides. I didn't take the reciprocal of that side, did I? 1 over m. That looks a little bit better. Okay, yes, negative delta is equal to 1 over m. And then we have delta is equal to negative 1 over m. Okay, so, and you can check that. And the reason why is we want delta to be small and we're expecting m to be large. So we found a discrepancy and we fixed it. So this is the delta that'll work. And the verification of that is right here in this equation and that picture. There's your proof. So let's write down this statement right there. Given m, what we say is given m, we say let delta be equal to -1 over m. Then we write then if this holds, then that, and that's good, and the verification is right here, and we're done. Thanks for watching.